In this video, we're going to talk about randomized experiment designs. The first type of randomized experiment designs are completely randomized experiments. So in a completely randomized design, the experimental units, so those are the subjects, the people, the animals, the things, are assigned to the treatments completely by chance. So this outline is for that group of 20 students who half of them were going to get caffeine and measure the pulse rate, half of them weren't going to get caffeine and measure the pulse rate. So we have volunteer students, we have a random assignment. Remember, you can use that using technology, slips of paper, plenty of ways to do it. Split them into two equal groups. The first one gets caffeine, the second doesn't, and then you compare the results. Something else to note is that completely randomized designs do not require each treatment group to be exactly the same, so you don't have to have 10 students here and 10 students here, but the assignment to groups must be completely random. And of course, having an equal number is preferable, but not necessary in completely randomized designs. So as always, let's follow that up with an example. This one has to do with chocolate milk and concussions. Let's read on. So, a headline read, "Concussion-related measures improved in high school football players who drank new chocolate milk." In that study, researchers compared a group of concussed football players given a new type of chocolate milk with a group of concussed football players who received no treatment. So, let's first explain why it isn't reasonable to conclude that the new type of chocolate milk is effective for treating high school football players with concussions based on this study. One thing that's possible is that the group who received the new type of chocolate milk knew that they were being treated and expected to get better. And so I wouldn't say that the improvement is because of the chocolate milk. So there were some other factors at play here, possibly. So the follow-up is to test the effectiveness of the new type of chocolate milk, you recruit 50 high school football players who suffered a concussion in the previous 24 hours to participate in an experiment. Let's write a few sentences describing a completely randomized design for this experiment. So let's structure something that is completely random to hopefully test this chocolate milk and concussions. So one thing you could do is number the players 1 to 50, use a random number generator to produce 25 integers from 1 to 50 without replacement, and give those players assigned those numbers that you drew the new chocolate milk. And then the other 25, give them regular chocolate milk. Compare the concussion-related measures for the two groups after both have consumed the same amount of chocolate milk. So while completely randomized designs are the simplest type of design for experiments, they're not always the best choice. Another choice is something that we call randomized block designs. So a block is a group of experimental units, remember those people, animals, things, your subjects, that are known before the experiment to be similar in some way that is expected to affect the response of the treatments. So a randomized block design is the random assignment of experimental units, again, subjects, to treatments is carried out separately within each block. So, for example, let's say that a smartphone company is testing two different keyboards, and they want to know which one users prefer or which are more user-friendly. And so they have 10 volunteers, so we start with 10 volunteers, but something that we know or something that we can find out before we conduct this experiment is who is a typical smartphone user and who is a non-smartphone user. So you can split up that 10 volunteer group into two blocks because we know something about each block. So let's say that there are 4 smartphone users and 6 non-smartphone users, and then they get randomly assigned, so each of those blocks gets split up. So 2 of the smartphone users use keyboard A, the one keyboard, and then the other 2 use the other keyboard, and that's a random assignment. And then we can compare typing speed for them, and then we'll do the same with non-smartphone users. So we split those 6 into 3 and 3. 3 goes to keyboard A, 3 uses keyboard B, we compare the typing speeds, and then we take all of those results, we combine and adjust for whatever it is that we need to adjust for, probably typing speed here, and we compare our data. So in this experiment, all of the users, all of the keyboardists here, typed the same phrase in the same kind of environment using a different keyboard, of course. And here are all of the responses. And that doesn't take into account smartphone users and non-smartphone users, and it's just their words per minute typing out this phrase. Now, keyboard A looks a little bit more successful, right? You get a faster typing speed there than keyboard B. But using a randomized block design, you can look at how that shakes out between smartphone users, so people who we would assume to be faster typers, and non-smartphone users, so slower typers, at least on the type of keyboard that they are testing, which is a smartphone keyboard. So the smartphone users are these little orange dots here, and of course they're faster typers, and the non-smartphone users are these black dots here. But comparing these two things, one conclusion you could draw is that keyboard A was more successful, or the keyboardists were able to use it more efficiently and type faster than keyboard B. And then you can adjust for the average words per minute of a smartphone user versus a non-smartphone user. So smartphone users, on average, type 14 words per minute faster than non-smartphone users. So when you take away 14 from all of the smartphone users so that they're at the same level as non-smartphone users, this is the dot plot that we get. So our smartphone users kind of are in the middle of the pack here, and they're kind of at the beginning and the end of the pack for the keyboard B. But still, keyboard A, I think, would be the choice that I would go with, at least using this randomized block design. So one thing that you can deduce from randomized block design experiments is that when the blocks are formed wisely, right, you take into consideration all the differences and similarities between the two blocks, it's easier to find convincing evidence that one treatment is more effective than another. So let's take that example and do another example. This one is, should I use the popcorn button? A question as old as microwaves. So the problem is, a popcorn lover wants to determine if it's better to use the popcorn button on her microwave oven or use the amount of time recommended on the bag of popcorn. To measure how well each method works, she'll count the number of unpopped kernels remaining after popping. To obtain the experimental units, she goes to the store and buys 10 bags each of 4 different varieties of microwave popcorn. So that's butter, cheese, natural, and kettle corn for a total of 40 bags. She must love popcorn. So first up, we're going to describe a randomized block design for this experiment. And oh yes, we're going to justify our choice of blocks. Here we go. So we're going to form blocks based on variety because the number of unpopped kernels is likely to vary by variety. Variety, again, is butter, cheese, natural, and kettle corn. So of the 10 in each variety, half of them, so 5 of the bags are going to get the popcorn button treatment and the other 5 are going to get the timed treatment. And we're going to place all 10 bags of a particular variety. So we're going to put all 10 butter in a box, and we're going to shake them up, and we are going to draw out 5 of them at random, eyes closed, no peeking, and assign them to be popped using the popcorn button, and the remainder can go to the timed instructions on the package. We're going to do that process for every one of the varieties, and so after popping each of the 40 bags, they better be a popcorn lover. It's a lot of popcorn. So after popping each of the 40 bags in random order, count the number of unpopped kernels in each bag and then compare the results with each variety, much like the dot plots on the smartphone keyboards. And then we're going to combine the results from the 4 varieties after accounting for the difference in average response. So essentially the average number of kernels left over. We need to adjust for any of those varieties having any outliers or anything that was extremely far off. We're going to account for that, just like we did in the last dot plot with the smartphones. And then we can compare each variety. And to follow up with the popcorn, let's explain why a randomized block design might be preferable to a completely randomized design for this experiment. A randomized block design accounts for the variability in the number of unpopped kernels created by the different varieties of popcorn. So that makes it easier, the randomized block design, to determine if using the microwave button is more effective for reducing the number of unpopped kernels. So when you have to account for variety, highly recommend randomized block design over a completely randomized design. The last type of randomized experiment design that we're going to talk about is something called a matched pairs design. And it is what it sounds like. A matched pairs design is a common experimental design for comparing two treatments that uses blocks of size 2. Lots of 2s, hence pairs. In some matched pairs designs, two very similar experimental units, so the subjects, are paired and the two treatments are randomly assigned within each pair. In other experiments, each subject receives both treatments in a random order. So of course, depending on what you are looking for, what kind of treatment you are giving, you might pair them differently as well as assign them to treatments differently. So essentially what happens, you got a pool of participants, and the first thing that you want to do if you want to use a matched pairs design to compare something between two people or two animals or two things, is you match the participant with its closest partner. Now that is going to depend on what it is that you are looking to match them by. Maybe it's height, maybe it's age, maybe it's preference for something, or distaste in something, right? So you match them with its partner, and then you assign them to whichever group you want, the treatment group or the control group, or you have both of them participate in the treatment and the control, of course separately. All right, one last example. Will an additive improve my mileage? So the problem says a consumer organization wants to know if using a certain fuel additive increases the fuel efficiency in miles per gallon, or MPG, of cars. A total of 20 cars of different types are available for testing. Let's design an experiment that uses a matched pairs design to investigate this question. And, let's explain our method of pairing. So essentially we are measuring if a fuel additive increases fuel efficiency or not. All right, so what we're going to do actually is give each car the same treatment, and each car is going to be its own pair. It's reasonable to think that some cars are more fuel efficient than others, so using each car as its own pair accounts for the variation in fuel efficiency in the experimental units. So one thing you could do is for each car randomly assign the order for which the treatments are assigned by flipping a coin. Let's say head indicates that you're going to put in the additive first, record that fuel efficiency, and then record it with no additive. And tails means the opposite. No additive first, and then you put the additive in. So for each car, record the fuel efficiency in miles per gallon after using each treatment and compare. That's one way to use matched pairs design. And that's going to do it for this video. Thanks for watching.